So having done that experiment, we saw an example of how certain reactants will limit the reaction from going further. Like I said, in the first bottle, the baking soda limited the reaction. In the second bottle, there was no limiting reactant, and in the third bottle, the vinegar ran out first, and so it was the limiting reactant for the reaction. And so just to make sure that you're clear on how limiting reactants work, let me write a simpler equation here. And this is a simple version of the combustion of coal. So we've got solid carbon here that combines with oxygen to produce CO2 gas, okay? So if we had 3 carbon atoms, but we only had 2 oxygen atoms, 2 oxygen molecules, sorry, which of these, would it be the carbon or the oxygen that's the limiting reactant in that case? In this reaction here, if we have 1 mole of carbon, how many moles of the oxygen molecule do we need? Huh? It's very quiet, I can't hear you. We have 2 oxygen atoms, but this is an oxygen molecule. So for O2, for every 1 mole of carbon, there's an understood 1 in front of this. We have an understood 1 in front of that, right? So for every 1 mole of carbon, we have 1 mole of O2, correct? So if I have 3 carbons, then for the full reaction to take place, how many O2s do I need?
3.
I need 3, right? But I only have 2. So which one's going to limit the reaction if this is the case? The O2 is limiting the reaction, right? Does that make sense? What if I did this? What if I did 3 and 3? Which one's the limiting reactant now? There's not one, right? We needed 3 O2s for every carbon. I needed 1 O2, and I've got that. I've got 3 and 3 of each. So there is no limiting reactant in that one. And then, of course, if I reversed it around and did 2 for the C, the carbon's going to run out before the full reaction can take place with that many oxygens, right? So carbon becomes the limiting reactant. Does that make sense to everybody? Okay. So that's what a limiting reactant is. It's the one that runs out first, that keeps the reaction from going further. So let me write down the definition of that. Limiting reactant. It's the reactant that runs out first, limiting the amount of products made. Because the way this reaction works is that if I have 1 mole of carbon and 1 mole of O2, it's going to produce 1 mole of CO2. Then if I have 2 moles of carbon and 3 moles of O2, how much CO2 is going to be made? How many moles of that?
5?
No? 2. Only 2, right? Because for 2 moles of this, for 3 moles of this, we need 3 moles of this to give us 3 moles of that, right? It's a 1-to-1-to-1 relationship. 1 mole of this combined with 1 mole of this gives us 1 mole of this. So if I'd had 2 moles of this and combined it with 2 moles of this, I get 2 moles of that. Remember, this is like an algebraic equation, right? If I multiply this whole thing by 2, then this equation becomes 2C plus 2O2 yields 2 CO2, right? And so if I had a 3 in front here, then it would be 3 C's plus 3 O2s would give me 3 CO2s. But what I'm combining together is 2 C's and 3 O2s, the most that I can get here is 2 CO2s because I don't have 3 Cs. I've only got 2 of those. So the C is going to run out and it's going to produce this with some extra O2 left over. All right, I'm not saying it's exactly 1 mole, but that's my point. We're going to have some oxygen left over that didn't react because there wasn't enough C to react with it. Okay? All right. Let's move on to do some examples. So if we go to page 210 in the book, we've got this problem is really no different from any of the problems that we've done before, but the language is a little different. So that's why we had to talk about limiting reactants so you wouldn't be confused if they identify a limiting reactant or they say we have excess of some compound. That's what they say here. Bless you. What they say here. So aluminum carbide, which is Al4C3, combines together with hydrochloric acid, 12HCl, or hydrogen monochloride, produce, bless you, 3CH4 plus 4AlCl3. And so what they tell us is that we have 83.1 moles of this, 83.1 moles of aluminum carbide with excess hydrochloric acid. And so they want to know how many moles of this and how many moles of this will be produced. Okay? So now that we've talked about limiting reactants, hopefully this word excess here won't confuse you when you see it. All that means is that we have an overabundance of hydrochloric acid, right? So we have enough hydrochloric acid to fully react with all 83.1 moles of this substance. So this is our limiting reactant, and that's the one that's going to control how many moles of this are produced, right? So that's all excess means. Don't let that confuse you. Just means focus. This is our limiting reactant, so that's the one that matters as far as the number of products that are going to be produced. How am I going to determine the number of moles of this if I know the number of moles of this? What's the relationship that's important? What conversion relationship matters?
1 mole of Al4C3 equals 3CH4.
Exactly. 3 moles of CH4. Thank you, Joey. All right. That's exactly right. Why did she say that? Well, because I had moles of this and I'm trying to figure out moles of that. So the relationship that the equation tells me between those two is that for every 1 mole of this, I've got to have 3 moles of this, right? And so now it's just a unit conversion, right? It's just saying I have 83.1 moles of Al4C3, and I'm going to multiply that times, I'm going to put the moles of CH4 on top because that's the unit I want to end up with. And I'm going to put the moles of Al4C3 on the bottom because that's the unit I want to cancel out. And so when I multiply that together, I get 249 moles of CH4. So the key to this was making sure that you knew that conversion relationship, right? Questions? No questions? Then you guys should be good to go on figuring this one out, right? What's the conversion relationship that's important to determine how many moles of this I have?
1 mole of Al4C3 makes 4 moles of AlC3.
Exactly. That's exactly right. That's the conversion relationship we need. So again, starting with the 83.1 moles of Al4C3, we're going to multiply that times, using this conversion relationship, I'm going to put my moles of AlCl3 on top, because that's what I want to end up with, and the moles of AlCl4 on the bottom, because that's what I want to cancel out. And those units cancel out, and I'm left only with moles of AlCl3, and I have 332 moles of those. So those are our two unknowns. Those were the answers that we were going for. So, I'll let you finish writing that down, and I'll ask you one more question. So I know I had plenty of HCl, right? It was excess. We had excess HCl. We had more HCl than we needed, right? But tell me this, can you tell me how much of the HCl was used up for this reaction to take place? We can figure that out as well, right? It's the same thing that we've already done, except this time we need the relationship between Al4C3 and HCl, right? So for every 1 mole of Al4C3, we need 12 moles of HCl. So then using that conversion relationship, we could figure out how much HCl was used up, right? Be the exact same thing we've already done, 83.1 moles of Al4C3 times 12 moles of HCl over 1 mole of Al4C3, and that comes out to be 997 moles of HCl. Was that all the HCl we had? No, because we had excess, right? We had more than enough, but this was all the HCl that was used up. So there was some leftover HCl after the reaction was done. Questions about any of that? Anybody want to know my favorite color? Questions about anything?
What is your favorite color?
See, that's a great question. Blue's my favorite color. Thanks for asking.
What shade of blue?
See, you ask a colorblind guy that, and it's kind of, I will tell you though, as being colorblind, it's like sky blue is my favorite blue, because that's like really easy to see when it's like a nice, I mean, it's sort of similar to, you know, that kind of lighter one there, but sort of like a lighter blue. Sky blue. Although, that's like Florida Gators blue is a little darker than that. I really like Florida Gators blue. I'm not necessarily a Florida Gators fan, but I like their blue, because I can tell very clearly that it's blue. There you go. More information if you want it. You're welcome. All right, let's move on to another problem, which is right across the page in the book. And it's basically going to be the same problem. If you've got this problem down, you'll be able to easily do the next one. But we need to make sure you're clear on these, because this is not going away anytime soon. Fe2CO3, the reaction they give us, plus 3C yields 2Fe plus 3CO. All right, so iron can be produced from iron ore, which is this, Fe2O3, according to this equation, all right? And suppose a chemist wants to make 100 moles of iron. So it wants to make 100 moles of this stuff. 100 moles of Fe. How many moles of Fe2O3 will he need? So how many moles of this do we need to make that many moles of that? And then how many moles of carbon will he need? How many moles of this will be required to make that much iron? And how many moles of CO? You know, they just ask us about all of them. But the reality is we're doing the same thing to find out all of those, right? We just have to use the correct conversion relationship. So let's start with this guy here. I know how many moles of that I want. How many moles of this do I need to start with? So my relationship between those two are 1 mole of Fe2CO3 is equal to how many moles of Fe? 2 moles of Fe. Does anybody at this point not see that? Do you not understand where I got that from? It's just the big numbers in front of each of these compounds, right? 1 mole of this is equal to 2 moles of that. And so now we just convert. 100 moles of Fe converts to moles of Fe2CO3 using this conversion factor. Moles of Fe cancel out, and so we have 50 moles of Fe2CO3. That's how many moles of this? 50. What about C? Well, for C, as it relates to Fe, we know that 3 moles of C equal 2 moles of Fe. And so then I can take 100 moles of Fe, multiply that times 3 moles of C, put that on top, because that's what I'm converting to, and put 2 moles of Fe on the bottom, that's what I'm converting from, so those units will cancel out. And so we get 150 moles of C. And then the last one it asks us about is how many moles of CO are produced. I would do the exact same thing, but this time I would say that 2 moles of Fe are equal to 3 moles CO. That's the relationship between these two. And I would do the exact same thing that I did here. Yes?
Sorry to backtrack some.
That's okay.
But to get the 2 moles originally, I'm trying to look at it and see from here. So you took the Fe2CO3, and because the 1 Fe2 on that side translates to 2.
That?
Okay, that might help me visualize it. I'm
Yeah.
sorry.
So that's okay. So yeah, there's an understood 1 there, right? So I just took that 1 there. That's where I got that 1 from. And I took this 2 here. That's where I got that 2 from.
So it's slowly just like bringing them down.
Just bring those down. Yep. That just read this as 1 mole of Fe2. That's the understood thing there. When you see the big 2 in front of that, read that as 2 moles of Fe. Okay? And so for this equation, 1 mole of this is equal to 2 moles of that.
Okay.
Right? And it's true for all of these. 3 moles of this equals 2 moles of that, which is what we used here. What we used here. 2 moles of this is equal to 3 moles of that, which is what we used here. So we're just taking those big numbers in the front and saying they're equal to one another. Okay? And then at that point, now that you've got, this is no different than, like I said, we know that 1 foot equals 12 inches. It's just a unit conversion at that point, right? And so if you had that right there, and I said, so how many inches are in 100 feet, right? Instead of moles of Fe, I said, if I said 100 feet, you'd just go, no problem, 100 feet times 12 inches over 1 foot. The foot cancels out, and so that's what, 1,200 feet. You know how to do that. That's all we're doing here. Huh? I'm sorry. I'm always checking you. Always got to make sure that you guys are paying attention, right? That's all it is. Yeah. All right. So it's just unit conversions. That's really all it is. We didn't do the last one here, but we could figure out the number of moles of CO based using this unit conversion. It's the same as this one. Right, so the answer is going to be the same. 100 moles of Fe. Based on this, we put moles of CO on top. Moles of CO, because that's what we want to end up with. We put moles of Fe on the bottom, and so our final answer is 150 moles of CO. That's our 3 answers: that, and that. Okay? Are there any other questions? I don't want you to, if there's anything that you're like, I don't know how he connected those dots, right? Just like you just asked, Nathan. Anything like that, now's the time to ask it, right? Because we're about to get more complicated. Yes?
So could 1 mole of Fe2CO3 equal 3 moles of C?
Yes. Yeah, so all of these are equal to one another throughout the equation. You can make You can do these unit conversion things with any of the items in there. 1 mole of this equals 3 moles of that. 1 mole of this equals 2 moles of that. 1 mole of this equals 3 moles of that.
And you can say that backwards as well.
You go the other way, yep, right. What?
So if you double the numbers on the left side, would that mean 4 mole Fe on the right?
So if I doubled the numbers over here,
Yeah.
if I doubled the numbers over here, since this works just like an algebraic equation does, if I were to double the numbers on this side, if I multiplied this whole side by 2, I've got to multiply this side by 2. So my resulting equation would be 2Fe2CO3 plus 6C will yield 4, multiply everything by 2, 4Fe plus 6CO.
Gotcha.
Okay?
Yeah. Thank you.
Now this is not, though, if I asked you to write the balanced chemical equation, that's not how you would write it, because you always want to write it in its simplest form. Since all of these numbers here can be divisible by 2, you would divide it by 2 to give it to me in its simplest form, right? But yes, if you doubled something on one side and you want to know how much was produced, you just double it on the other side. Okay? All right, good questions. Starting to click? Yeah? All right, well, let's get a little more complicated. All right? Which is the story of this class, right? You learn something and then we make it harder. But here's the reason why we have to make this one harder. When we measured out how much baking soda we needed for our experiment back there, did we measure out a certain number of moles of baking soda? No. We don't have a scale that measures number of moles, right? Our scale measures grams. And so in the lab, I'm working with things like grams and milliliters of substances, right? And so it's going to be useful for me to talk about these things not in terms of moles, but in terms of grams. All right? And so that's what we're going to do now. We're going to move from moles to discussing number of grams. We're going to start off with number of grams, and you need to tell me how many grams I'm going to end up with. All right? And so that goes. We know how to do that already. You just maybe haven't thought about it. What's the relationship that we're already aware of that will show us how to relate grams of something to moles of that same compound? What do we use to go from grams to moles or moles to grams? If we're looking at, say, for example, H2O. If I have 2 moles of H2O, how are you going to tell me how many grams that is? By finding the atomic mass, right? That's the way that we know to do that. That's our relationship between grams and moles. So that's what we're going to use. The molar mass, right? Ultimately is what we're calculating. How much? What's the mass of 1 mole? So let's do example 7.7. PCl5 is used in the manufacture of some pesticides, and it can be produced as follows. We take solid phosphorus, and we combine it with chlorine gas, 10Cl2. That's an O, a 0 there, not an O, as a gas, to produce 4PCl5. And so if a chemist needs 975 grams of this stuff, how many grams of Cl2 does she need? If I need to produce this many grams of that, how many grams of this do I have to use? So the problems that we've done in the past is I'd say I need this many moles of this, and how many moles of this do I need? So we know how to do mole to mole, right? But like I said, because we know how to use the molar mass to find a relationship between moles and grams, we actually already know how to do this problem. And so here's the way that you do it. When you start off with grams of one substance in a chemical equation and you need to end up with grams of another substance, this is the path that you take. You take the grams of the first substance, substance A, and you convert that to the number of moles of substance A. And then what we just did in the last problem is we converted from moles of substance A to moles of substance B, right? We've got that down now. But the problem didn't ask us for how many moles, it asked us for how many grams. So then we have to use the molar mass of substance B to calculate the grams of substance B. So that's the path we're going to take to get to the end of the problem. Does that make sense to everybody? Take this guy, convert it from grams to moles, and then once I have number of moles of PCl5, I can convert from that to moles of Cl2, and then once I have the moles of Cl2, I can convert from that to grams of Cl2. Here's the important thing to remember. You cannot go from grams of this to moles of this, or directly from grams to grams. You have to take this path of grams to moles. Then stoichiometry has taught us that we can go from moles of this to moles of that. Then you can convert that to grams. All right? So let's see. The first thing that we're going to have to do is we've got to convert this substance A from grams to moles. And so we do that by using the molar mass. So for PCl5, its molar mass is the atomic mass of, we have to find the atomic mass of phosphorus. What is that?
30.97.
34 what?
No, 30.97.
30.97. All right. And then what is it for Cl?
35.45.
Plus 5 times 35.45. Does that look right to everybody? Does that look correct? All right, and 208.22. 0.22 is how many AMU that is. So now I know the molar mass of PCl5. I know that 1 mole of PCl5 has a mass of 208.22 grams. That's why we find the atomic mass, so we can determine the molar mass. Now I have a conversion relationship that will allow me to go from grams of this substance A to the moles of substance A. So let's do that. We started off with 975 grams of PCl5, and we want to convert that to moles. So we use that and we say put moles on the top. PCl5, that's 1, 208.22 grams of PCl5. So that's going to equal 4.68 moles of PCl5, right? So we've made it to this point. We've got moles of substance A. Next step, go from moles of substance A to moles of substance B. In our case, which compound is substance B? Cl2, right? That's what we're trying to find, the grams of Cl2. So we're going to go from here to moles of Cl2. What's the relationship that we know between Cl2 and PCl5 in terms of moles?
10 moles of CO2 equals 4 moles of PCl5.
That's
Could
exactly.
you simplify that? Or does it have to be that many?
You could,
Okay.
like in other words, divide both by 2 and say it's
Yeah.
it's a 5 to
Yeah,
2
I didn't
ratio.
know if
You could do that.
Okay.
Yes.
In that 10, I thought the 0 was supposed to be an O.
No, I put a slash through it. When you see this through an O, it means 0 versus capital O.
I thought it was the other way around.
Yeah. No, it's in fact some calculators will have that on there. They'll actually have the slash through the O. So, but yes, thank you. I was trying to not be confusing, and I ended up being confusing. So yeah, I didn't want you guys to think that this was 1 in oxygen or something like that. You know. All right, so this is exactly right. This is the relationship that we need now to convert from moles of PCl5 to moles of Cl2. So let's do that. So 4.68 moles of PCl5, right, times, we're going to put moles of Cl2 on top, 10 moles of Cl2, 4 moles of PCl5 on the bottom. This is why you could simplify it, because 10 over 4 is the same as 5 over 2, right? But I wouldn't fool with doing that when I'm writing these down. I would just copy it down directly so you don't get confused somewhere. And so that's going to turn out to be 11.77 moles of Cl2. So we're so close, right? We're now at this step. We found the moles of substance B, but it asked us for the grams of substance B. So one final step. So now that I have moles of this, I know that we have 11.7 moles of this substance. How do I go from moles of that substance to grams of that substance? I use the molar mass, right? So I got to figure out the molar mass of Cl2. So Cl2, and I'll do that over here. Cl2 has a molar mass of 2 times, we said Cl was 35.45. So that equals 70.9 AMU. So that tells me that 1 mole of Cl2 is equal to 70.9 grams of Cl2. So that's the last conversion relationship that I need. And so now I can convert 11.7 moles of Cl2. I can convert that to grams using this relationship, 70.9 grams of Cl2 over 1 mole of Cl2. And when I punch that in my calculator, I get 8.30 times 10 to the 2. Since I'm not stressing over significant figures in here, we're just going to write it as 830 grams of Cl2. Does that make sense to everybody? And you may have even gotten another number. He's probably rounded here to significant figures. What was the actual number when you punched that in your calculator? Anybody do that? $11.7 times 70.9.
529.53.
What was it?
829.53.
829. So yeah, it rounded to 830. That's fine. All right. But if you had put 829 point, you done 2 decimal places or whatever, I'm not going to count that wrong. Any questions about this path that we followed to get there? Remember this. Commit this to memory. Right? Take the grams of one substance A, convert it to moles of substance A. Then from there we can convert from moles of substance A to moles of substance B. And then using that, we can convert to grams of substance D. That's how you convert from grams of one compound in a chemical equation to grams of another compound. And what I'm shocked about as I'm looking at my notes is that I didn't write that down in my notes. I can't believe I forgot to write it down because we're going to use that over and over and over and over. All right, we'll do one more problem and we will be done for the day.
Mr. Walker?
Yes?
Should we memorize that up on the top, right?
You should, if you need to memorize it to remember what the path is, then yes, right? I'm going to give you problems like this where I say you've got this many grams of one substance and you need to tell me the grams of this substance over here. And the way that you do that is by remembering that that's the order in which you tackle that problem, right? So if it just makes sense to you, then no, but yeah, if it's not clear, then remember that. Memorize that. The point with that is you can't, there is no arrow, right? There's no arrow from here to here. You can't do that. You can't go directly from grams to grams. You have to go to moles first, then moles to moles, and then from mole to grams. Now sometimes I might give you a problem, or you might have a problem in the book where you don't have to do all of the steps. You know, maybe he gives an equation and he says, I've got this many moles of the first one. How many grams is that going to give me of the other substance? So you can start right here, right? You get to skip this step. Or maybe we give you grams at the beginning and say, tell me how many moles of the other substance we need. So you get to stop at that step. You know, so it could be a little bit shorter depending on how the problem reads, but you need to know how all of that works out. All right, problem 7.8 is our last one. And it says, we're given this chemical equation, 2 FeTiO3 plus 4 HCl plus Cl2 yields 2 FeCl3 plus 2 TiO2 plus 2 H2O. And it says if we have 15.5 kilograms of this and excess, and we've got a bunch of extra HCl and a bunch of extra Cl2, how many grams of TiO2 can be made? So grams of this. All right, what does, when they tell us excess, what does that mean? It means that's not important, right? The limiting reactant, this is the limiting reactant then, and this is the one that's important for our calculations, right? And as it turns out for this problem, since we're trying to go from the amount of this to the amount of this, those are really the only things that matter in this equation, right? There is one problem we have in this one that we didn't have in the last one. Does anybody know what that is?
If you convert from kilograms to grams.
Exactly. We know how to convert from grams to moles, which is our first step here, but we can't go directly from kilograms to moles. We're first going to have to convert from kilograms to grams, then we can begin our process over here, right? So 15.5 kilograms of FeTiO3 is going to be equal to, how many grams are in a kilogram? 1,000. So we need to find out, we need to put grams on top. We have 1 kg on the bottom, and so that's going to come out to be 15,500 grams of FeTiO3. All right, so now we're ready to go from grams to moles to moles, and moles to grams, right? Now we're doing the exact same problem that we did before. All right? And so what we actually could do is we could find out all of those conversion relationships up front that we're going to need for this problem, right? The things that we're going to need is we're going to need the molar mass of this, the molar mass of this, and then how many moles of this are equal to how many moles of that. So those are the three things that we need. So we'll go ahead and write down the mole to mole thing first. 2 moles of FeTiO3 are equal to 2 moles of TiO2. All right? 2 moles of this equal 2 moles of this. That's one thing we're going to need. We're going to need the molar mass of FeTiO3. So I'm going to put a square around this so we remember we need that. FeTiO3. What's the atomic mass of Fe?
55.85.
55.85 for Ti.
47.
That's for Fe.
What now?
Fe was 55.85.
Oh yeah, but T. I'm asking for the next one. So Ti. That's okay. What was Ti?
47.87.
47.87, and then oxygen is 16, so that's going to be 3 times 16 for that last one there. So when we multiply and add everything up here, we get 151.72 AMU. And so our molar mass, 1 mole, in other words, the mass of 1 mole of FeTiO3 is equal to 151.72 AMU. So there's another conversion relationship we're going to need. I'm sorry, I did that wrong. I'm glad I looked at that. I meant to say grams right here. Grams of FeTiO3. That's what happens when you start thinking ahead in the problem about what you got to do next. All right, any questions about that? Find the molar mass? You guys pretty much got that down now, right? Straightforward. So what's the other thing we need to find the molar mass of?
2TiO2.
Not the 2, ignore the 2 in the front here, but just we need to find the molar mass of TiO2, right? So TiO2 has a molar mass of 47.87 plus 2 times 16, which equals 79.87 AMU. 79.87 AMU. And so then 1 mole of TiO2 is equal to 79.87 grams of TiO2. So now we have all the information we need to do this entire problem. All right, so remember how I told you that I like to do my conversions like this because I can actually string them along and do several conversions together. So I'm going to do that, all right? If it's confusing to you, you don't have to do it that way. You can do it like I did in the last problem where we converted one to the other and we wrote that down by itself, and then we took the value we got there and we did another conversion, right? And then we took that value and we did another conversion. We can do it like that. But I like to, we know we're converting from grams of this stuff, right, to grams of the other stuff. So I'm going to write grams of this down on this end, and we're going to do one long big problem, all right? 15,500 grams of FeTiO3. And I want to show you just how, whenever you have all the stuff that you need to do the conversion, that it really is just a big unit conversion, right? So I start with grams of substance A, and I convert from that to moles of substance A. So here's my relationship between grams and moles of FeTiO3, so TiO3, so I'm going to use that. I put grams on the bottom, 151.72 grams of FeTiO3, and I put moles on the top, 1 mole of FeTiO3, right? I just used this, and I figured out which one to put on the top and the bottom based on what I was converting to, right? So when I do that, grams of FeTiO3 are going to cancel out with one another here, on the top and the bottom here. And so I'm going to be left with moles of FeTiO3. Well, from then, so that's moles of A over here. From that, I need to convert to moles of B, right? Which in our case is TiO2. So I'm going to use this equation, that conversion relationship. So I want to end up with moles of TiO2. So I put that on top, and then 2 moles of FeTiO3 I put on the bottom. And so my moles cancel out there with FeTiO3. And I'm going to be left with a unit of TiO2. So now I've made it all the way to here, and just need to convert from moles of substance B to grams of substance B. And for that, I'm going to use this relationship, right? So I put the grams on top, 79.87 grams of TiO2. And I put moles of TiO2 on the bottom. So my moles of TiO2 cancel out, and I'm left with a unit of grams of TiO2. So now I just take my calculator, and I can't punch all of those values in, right? And my calculator's not in here. So I say 15,500. 15,500 times my 1 here times 2 times 79.87 divided by 151.72. 1.72. I just have to make sure with all of these on the bottom I do divided by those. Divided by 2 and divided by 1, which we don't have to do. So I get an answer of 8,159. Is that what you got in the book? 8,150, right? So On mine, I would round up to 8,160 grams of TiO2. Why is his number different from mine? It has to do with the significant figures, right? He's taking all that stuff into account, but I told you guys I don't want you sweating that. I want you to get these concepts down instead of worrying about significant figures all year. So this number is a little bit different, but there was, to me, by laying it all out like that, there was sort of less room for error. If this is confusing to you, don't do it. I also kind of think this is just neat. You know, it's real easy for me to see what cancels out and all of that. But if that's confusing to you, please do it like I did in the last problem where you do it in chunks. Okay? Any questions? All right, for those of you that aren't brave enough to ask me in class, I will be here a little bit after class cleaning up, so let me know if you have questions. All right? Y'all have a good week. No class next week, Thanksgiving week, right? So we'll be coming back. I'll be handing out a test next time. Don't forget to do your lab. Y'all have a good one.